Good afternoon, everybody. Welcome to this week's colloquium of the C3.ai Digital Transformation Institute. And just to recap, it's our job is to have intellectual thought discussion about the science and technology for the digital transformation of business, government, and more generally societal systems. It's a partnership funded by C3.ai and Microsoft, Berkeley, Illinois, Carnegie Mellon, the Royal Institute of Technology, Stockholm, the Lawrence Berkeley National Labs, MIT, the National Center for Supercomputing and its applications at UIUC, Princeton, Stanford, and the University of Chicago. And this particular colloquium is ongoing. The speakers next week are Anna Harton and Jonathan Osick from the University of Chicago, talking about health inequities and caused by COVID. And then Mattis Teglarski is going to be talking about deep networks. And this is the mathematics of deep networks. Devaka Shukla will talk about scanning of interaction. This is really about the mechanisms by which the spike protein infects human cells. Christian Borgs, network science, will talk from Berkeley, will talk about algorithmic design making and dynamic learning. And Nathan Schrebro will again talk about the mathematics of deep learning. The mathematics of deep learning is getting to be a very exciting subject. And I hope you will find use with these. Stefano Parasco will talk about architecture, really about how do you use light to maintain the kinds of social distancing that will be needed as we come out of the pandemic. Stefano Soato from UCLA and Amazon will talk about differential learning and also the mathematics of deep learning. Jeff Shama will talk about the rapprochement between adaptive control and learning. And Louis Shaw will talk about distributed systems, embedded systems, and COVID-19. And the series is ongoing in June and so on. The presentations are on the website, on the YouTube channel. We are in the process of updating the slides, and then we also have been collecting transcripts of the more recent talks. So we'll be posting them soon. They're to appear on our website. I want to plug this, in addition to colloquia, we also have workshops. The fourth of these workshops is going to be next week. The organizers are Asuman Ozdaglar and Alexander Madri and Sarah Amin at MIT. And they're going to be talking about how do you take this digital transformation and apply it to socio-technical systems. It's really an exciting program. They have people on networks, people on network science from Cornell, and economists from Stanford and University of Chicago. And it's really, the format next week, I have to say, will be short talks and long discussions. So please see if you can do this. We have a second call for proposals out, which is on digital transformation for energy and climate security. And with the recent announcements that people are making, Shell promises to decarbonize by 2050. And, with all the announcements that are being made, the use of AI for carbon sequestration, for risk assessment, all of those, these are getting to be really wonderful topics. It's the stuff of op-eds in the New York Times a couple of weeks ago. And so anyhow, I hope you will bid on this. The proposals are due March 29th. This presentation is 40 minutes long. The Q&A feature, I think Camille will keep us straight in terms of these questions. And so let me not detract too much from the main building structure into deep learning, which is also along this theme of, I'm really very pleasantly impressed to see the kind of analytics that is going into what used to be really complicated networks to analyze. So Zico is our speaker this afternoon. Zico is an associate professor and the chief scientist of the AI Research Lab at the Bosch Center for Artificial Intelligence. And, he has a number of awards, and I'm going to, instead of sort of telling you about his formal awards, which are quite considerable, he has a DARPA Young Faculty Award, Sloan Fellowships. I should tell you about my own experiences of working with Zico. Zico used to, when he was finishing his PhD, was at Stanford, was working on this disaggregation, which is how do you take a look at smart meters and decide which which devices are on in a household. And I first heard about what Zico had been doing, I thought this is really impossible. And so I got talking to Zico just because I just didn't believe that what he was doing was actually possible. And with the use of some wonderful learning techniques to do energy disaggregation, he has since, of course, moved on from all of that. I have to say, he also worked as a consultant for C3.ai through some of the most early phases of this, and he really has helped shape a number of the C3.ai programs. So it's, I think you're in for a treat, because I have complete confidence that you'll be as enthralled with Zico's talks as I have been over these years. So welcome, Zico, and I will mute myself, relinquish my screen, and all of that. Welcome, Zico.
All right, thanks very much, Shankar, for that wonderful introduction. I hope to live up to your billing here. It's always a challenge. Thanks, everyone.
I'm sure you will.
We'll see, right? Well, you can tell me afterwards whether I've lived up to it or not. So hi, everyone. Thanks very much for coming here. It's great to be here. Let me share my screen now. Let's go. All right, and arrange the windows as I want here. It's always hard to do that with Zoom. They put it back every single time anew. All right. Okay, wonderful to be here. I'm going to talk today about building structure into deep learning. And as Shankar mentioned, I actually would prefer a little bit, if possible, we'll see if it's possible, but go ahead and ask your questions during the talk. I know it's technically 45 minutes, 40 minutes for the talk and 45 minutes for questions, but with Camille's permission, maybe I can interrupt some of the talk time to also take questions during the talk. I just find it leads for a much more dynamic talk if people are asking questions. So please just go ahead and ask questions during the talk. We'll see if it works. If it ends up that I can't pay attention jointly to these things, then we'll pause and maybe do them more at the end. But I really hope to be able to answer questions throughout the talk. This is really joint work with some of my students. So in particular, the main collaborators here are Priya Donti, Brandon Amos, Po-Wei Wong, Philippe de Avila Perez, and Melrose Roderick, but many others as well at other institutions, sort of across the world in some sense. All right, so let's start out. And to start out this talk is about building structure into deep learning. So what do I mean by this? Well, if we think about the sort of past year in AI, I occasionally remake this slide every year, and I find that I'm never at a loss for things to put, because it turns out every few months in AI, I find something that kind of shocks me, that surprises me, that I didn't think was possible, that all of a sudden is possible. And this is one of the wonderful things about working in this field, is that I can be frequently surprised, despite in many times sort of knowing how the technology works, at least to a certain extent. I still find myself constantly surprised by the capabilities and the innovations that we're making as a field. So as a few examples, I'm sure many people here heard about AlphaFold, that solved is a strong word, but the extent to which they improved over the span of 4 years upon the state of the art in protein folding is really amazing. So the system that developed a DeepMind was able to predict the 3D structure of proteins from their DNA sequences, and it really is sort of this is one of the a foundational problem in biology and chemistry, and it really, they've done an amazing job at doing this, and I was sort of blown away by seeing the progress they've made there. Maybe a little bit less scientifically relevant now, but still, when it comes down to it, amazingly cool. There was some recent work by OpenAI on a method called DALL-E, which generated images from text. So you can give a text prompt like an illustration of a baby hedgehog in a leather jacket using a calculator. Now there are not that many images of this in in the world of Google, and you can of course play around with this and check different ones as well. Though it is curated, to be honest. I'm not. We'll see how much this really stands up, but it's amazingly impressive, right? You sort of enter this thing. It trains a sort of on a bunch of captions and corresponding images, is able to train a system that, given this prompt here, can actually generate and make images of this thing. These techniques are both based upon advances in deep learning, and at least in the case of DALL-E, they haven't had a full paper yet on AlphaFold 2, but in this case on DALL-E, I've read the paper, I understand the system works, and it still amazes me just how cool the combination of these techniques with massive amounts of data, and just how much this can really do in practice. I wouldn't have thought this was possible even 2 years ago, either of these two things. Now, going to the theme of the workshop, though, or this whole series, there's a lot of focus on COVID too. So I should also mention that there has been a bunch of work on applying AI techniques to COVID-related problems. The one that I'm actually probably most familiar with, just because it's from CMU, is the COVIDcast project, which is led by the CMU Delphi group, on essentially using data from many different sources to get a sense of the current kind of snapshot of what our situation with regards to COVID actually looks like on a county by county level in the US. And this is also amazingly impressive. So our ability to aggregate data, to integrate these sources together, and to provide it in sort of a useful way like this. Though I should mention that there's no deep learning here. I think maybe there's been some since I was involved, but at least when it comes to what I'm aware of, this is largely sort of a simple statistical analysis. Well, I shouldn't say simple. The mathematical tools or the mathematical models that they use here, compared to some of these more deep learning models, are relatively simple. And so the question, of course, is why is this? Why are we able to do such amazing things with deep learning? And in some cases, I don't actually want to downplay the impact that deep learning things have had on COVID applications, because there are definitely many, including many talked about at this workshop and other series. But I think at the same time, there is an extent to which these systems are not as prevalent in what you're seeing kind of as real domains. And I want to know why that is. And so to answer that, I want to sort of look at what machine learning models actually are. So what a machine learning model is, the way modern machine learning works, is that we have some input data to the system. This input data is then transformed by a bunch of layers. And this is a cartoon. Of course, this is more complex in practice. And these layers transform into some output. And then based upon the output and maybe a real label of the system or some other information about this example, we suffer some loss. So we give it some sort of objective to the system. And then to minimize, and then what we try to do is we try to adjust parameters of this model to minimize this loss. And this is how deep learning works in a nutshell. The problem here is that when you want, this is sort of amazingly good at modeling very complex phenomena like protein folding or like image generation with a lot of data when you don't have much idea about how the system works. But the reality is that there are many problems which we do know how the system works very well, or there's some logic that we want to actually encode into the system that we have as prior knowledge. This is how the vast majority of engineering actually works. So what we want to do, for example, is we want to maybe give some structural specifications for the input data. We know it's going to come with certain constraints attached to it. We want to somehow encode those into the machine learning algorithm. Maybe we want to, inside the network, enforce things like hard physical constraints. If we are modeling some physical system, well, we actually know the laws of physics pretty well. Maybe we want to somehow incorporate those into the nature of the machine learning algorithm. Or maybe we're going to take the output of this algorithm, and we're not just going to use it kind of blindly. We're going to actually incorporate the output of a prediction system into some other decision-making procedure. Oftentimes a very well understood one based upon optimization and things like this to actually do something with these predictions in an automated fashion. Yet most machine learning systems don't really deal with this. They don't really care about what is being done with their outputs other than as it pertains to this loss function trying to minimize, which is often just something like prediction error. And so how can we start to integrate what we want here into deep learning systems to actually make them more amenable to these problems where we have a lot of known structure in the system. This is what this talk is about today. And so to give one example of this, I actually want to highlight a simple example from sort of a illustrative use case for ML methods. So I'm going to use one particular example of energy scheduling domain, which will give a few more results on later. But really, this is a very common paradigm that applies kind of across the board. So the input to a machine learning system is some data. And I'm going to use the example of predicting, in this case, electrical demand. And so in that case, the input could be something like weather data, right? Because weather affects how much power people are going to consume. So maybe we want to use the weather to predict these things. That's our input data to our system. Of course, this, after we train the system, we will also give it to train the system, we'll also give it the true sort of ground truth consumption. But at runtime, what the input to the system is sort of this weather data. We would then use that to build some or to make some machine learning prediction, i.e. a forecast. And in this sort of example, the forecast could be something like electrical demand. But we don't stop here, right? What we actually do is we use these forecasts and we feed them into some other system, right? Like an automated decision-making procedure, which uses optimization. For example, optimal power dispatch. And then we, from this actual dispatch, we suffer some cost, right? So for example, CO2 emissions. If you schedule power badly, you have to ramp up power at the last minute. That might be more costly in terms of emissions, getting to the points that Shankar made earlier as well. The problem with machine learning methods is that all this structure in the problem, they kind of ignore. They ignore the physics of weather, for example. They ignore the cost that's incurred after the fact. All they're trying to do is just kind of maximize their own prediction accuracy. But what I will argue for in this talk is a more holistic kind of end-to-end approach. Truly end-to-end, I think. Machine learning uses that term a lot to mean something different, but a truly end-to-end approach. Where, for example, what we can do is feed back. If we can actually incorporate, our decision-making procedure, for example, into the model itself, maybe we could actually incorporate the true domain costs into our prediction method to adjust our model, not just to be more accurate, but actually to reduce emissions when that model is used in this whole end-to-end chain. So that's the kind of idea that I want to get at here. This is just one example, and there are many other applications which I'm going to highlight here. But this is the core idea. We want to integrate this kind of structure into machine learning systems. Any questions so far? That's been I guess it's just introduction so far. I am monitoring the questions still, so do feel free to ask them. All right, so with that as background, I'm going to go through sort of three sections, or really two main sections, and one bit of final thoughts in this talk. I'm going to talk first about a technical tool that we're going to use to incorporate these sorts of layers into machine learning systems. And then I will talk, which is going to go in the name of implicit layers. I'm then going to talk about a number of applications we have on implicit layers, specifically in regards to building structure into these models. And so there's actually many other applications of implicit layers, and this is a very, very broad field. But I want to focus today on the applications of incorporating structure into deep learning models. And I'll have some final thoughts. So this is going to be our quick outline. It's largely going to be kind of mostly high level, but I will provide a few slides of details for those that are sort of eager for a little bit of math in the audience here. All right, so let's talk first about implicit layers in deep learning. All right, so if I talk about a layer in a deep learning system, chances are most of you will think about something simple. So we think of a layer, when we think about a deep learning system, you think about individual layers in that system being composed of sort of simple, almost atomic operations. I guess, depends on your definition of atomic, but very simple operations. Things like a matrix multiply, a convolution, a ReLU operator, etc. These are all very simple sort of modules that we then hook together in very, very complex ways to get things that you saw before, like AlphaFold or like DALL-E that creates images from text. And sometimes it's actually kind of amazing that that's possible, right? It's amazing that we can actually just hook together a bunch of mixed multiplies and get out and a bunch of ReLUs or attention layers and get out image generation. But that's how systems work. That's how these systems work for the most part. However, the way they get this power then is by chaining together many, many very, very large layers that as a whole then are sort of, there's no real intention to them, and there's no real structure that we can, or there isn't much structure we can impose and encode within these layers. So the point I want to make, and then the main technical point of this talk, is that we're not limited to thinking of layers as these simple operators. We can also think of layers in deep networks as fairly complex, meaning complicated, though they also could be complex in the mathematical sense, but complicated computation units. A layer can be something like an optimization procedure itself. So solving a problem as a layer. It can be something like a fixed point computation. It could be a simulation. It could be an ODE solution or a PDE solution. Those things are all perfectly valid to think of as layers. They are all parameterized functions that have some input and output. But in order to do this, in order to think about these things as layers, it requires that we introduce what we call the notion of an implicit layer. And the basic idea here is actually quite simple. If we think of an explicit layer, it's a little bit actually almost just definitional here. But if we think of an explicit layer as some sort of direct mapping of the input to a layer, which I'll call X, to the output of the layer, which I'll call Y, then we think of most layers as kind of, in deep learning, it's kind of specifying a definite computational graph for how we compute that output from the input, right? You take the input, you multiply it by a matrix, and that's the output. That's how we typically think about layers. What I'm going to think about instead is what we call an implicit layer. And the idea here is that we're going to just frame the notion of a layer slightly differently. Instead of talking about layers as being kind of a functional mapping from input to output, or a computational graph that specifies how you map from input to output, we're going to think of a layer as sort of solving some root finding equation in some sense. We're going to think of a layer as taking, again, some input X and producing an output Y, but the only condition here is that the X and Y jointly have to solve or satisfy some nonlinear equation. And I'll give a lot of examples of this in a second, but it turns out that this sort of simple trick here is an incredibly powerful tool, because it turns out you can actually formulate most of these problems, optimization, fixed point computation, et cetera, precisely as finding the solution of an implicitly defined layer. And there's a lot of very nice things about this, which I'll get to in a second. Of course, to actually compute Y from the input, you need to provide a solution procedure, which is a computational procedure, but it can be a very complex one. It can involve iteration. It can involve lots of sort of complex internal operations that you can kind of actually ignore from the standpoint of the layer itself. And I'll describe in a second how that works. But that's the sort of the shift that we're going to make here. Is we're going to kind of redefine what we mean by a layer in deep learning. Now, in order to make some function like this a layer, though, in deep learning, it requires that we actually do two things. So most deep learning systems work require, I should say, sort of two passes in our data. Sorry, I shouldn't say our data. They require two passes through the network, which have the following names. There's first the forward pass, and the forward pass actually is just sort of solve this equation here, is what it means, really. So a forward pass in a network, what that means is for each layer, the layer is given some input, and you have to compute the output of that layer. So in the context of sort of computational graph layers or explicit layers, this is really easy. You just run that computational graph, and you have your output of the layer. In the case of an implicit layer, though, what we said before was that implicit, and I'll give some examples of this in a second. We said that implicit layers, what they do is they require us to sort of use some iterative procedure typically to solve for a Y that satisfies this equation. But the thing with this is that any of those methods we talked about before, whether they be optimization problems or ODEs or PDEs, they already have this huge wealth of solvers that are already out there that precisely solve this fixed point equation, or this sort of root equation for that problem of interest. And so we can just use those solvers that are already out there to sort of solve for our output of our layer and kind of be done. So whatever you want your layer to be, if you want it to be an optimization solve, just call some optimization solver. If you want it to be a complex PDE simulation, just call that PDE simulation, etc. So the forward pass is kind of the easy part. That's the easy bit. That's how we just compute the output of the layer when we're running the network forward. Now, one thing I want to emphasize is this is actually going to make the networks often more computationally intensive to compute. I know deep learning already has this reputation for being very computationally intensive. I'm actually not really solving that, right? I'm actually potentially making it more complex because I'm introducing an optimization problem that we need to solve actually every time. Every time we actually want to run the network forward. Yeah, so someone asked, is an implicit layer different from an explicit layer because it functionally requires recursion? Was a question asked in the discussion. And let me answer live. Okay, here we go. So it doesn't have to require recursion. It can just require iteration and things like this. But the point is that at the specification of the network, we actually don't care about how we find the solution. The layer itself, I mean, computationally has to sort of compute it at some point in the forward pass, but we're defining the network, kind of ignoring the question about how we compute that solution. That's really the key point. And in doing so, because you can formulate basically any problem when it comes down to it as a root finding problem, it's a much more powerful single operator that can embed a lot of structure into these networks. And I'll give a bunch of examples later on in the second half of the talk. Yeah, so someone asked, what if a feasible solution does not exist? So if there is no Y that does this, you have to take care for that, right? Because unlike matrix multiplications, where we can always multiply a matrix, right? You can always do that. If the solution doesn't exist, then yeah, what's the output supposed to be? The solver will say, infeasible, can't solve it. So you have it is when you specify these things, you should take care to specify them in a way where there is always an output, or at least hopefully in practice, you will always be able to find an output. And you can specify that by basically ensuring that you specify your optimization problem or your ODE or your PDE or however to actually be one that has a solution. But it does require some care. Fortunately, if you're modeling things like physics and stuff like this, there usually is some solution to physics or the world couldn't function as it does, right? So you can typically do it, but it does take some more care in creating our network. But it's things that we kind of want to do anyway. Yeah, and so someone asked, the G can be much simpler than the function that solves for G. That's a great way of putting it, is that we can encode the structure simply, even if it's capturing a very complex phenomena, right? I can very easily write the Navier-Stokes equations. They are very hard to solve in practice, though. Okay. All right. So someone's asking, okay, getting a lot of questions already, great. Yeah, so let's talk about parameters then, because I'm going to talk about parameters in a second. So the theta are the parameters of the layer. And let me talk about actually how the backward pass works, because then I'll sort of talk about that. So here's what we need. So in order to compute in order to integrate something as a layer in a deep network, it is required that we be able to compute not just the forward pass here, but also a backward pass. And that means we can compute the derivatives, or more strictly the Jacobians, or even actually more specifically the vector Jacobian product, because we're computing the back propagation. So if that makes sense, that's great. If it doesn't, don't worry too much. We have to compute derivatives of the layers. That's how deep learning works. We train it with gradient-based methods, so you need to be able to compute the derivative kind of through this implicitly defined layer. And that involves sort of two things. It involves being able to compute the Jacobian of the output of this layer with respect to the input, and the output of the layer with respect to the parameters theta. Where here, what I mean by parameters, I think this hopefully answers the questions that were asked. The parameters of this network are actually the exact same. They're just like the weights in a normal layer. They are essentially the terms that define whatever optimization problem or ODE or anything else you want to solve. They can be very generic. So they can parameterize a generic, say, quadratic program or something like this, or they can be very specific and parameterize a single regularization parameter in an optimization problem. We are free to specify the parameters of what we want to be a parameter and what we want to be fixed. And that's actually the beauty of these things, is that they're very flexible and sort of allow you to learn whatever you want to learn, whatever parameters you want of your optimization problem, you can learn, and what you sort of know, you can leave as known. That's kind of the beauty of this to a certain extent. So the big question, though, is how do we compute these? So for explicit layers, I kind of know how to do this, right? I can compute these pretty easily. For implicit layers, it's not so obvious. Once I've even found a solution, how do I actually backpropagate through this layer? And for that, oops, I'm back to the Zoom here for a second. I'll sort of have the one kind of slide with a bit of math in this talk here. There isn't much math here in this talk, actually, but it's a little bit. And it's about how you compute this Jacobian. Though I have to say, this is extremely simple math. It goes back about 200 years, so I'm hardly breaking new ground here. So I hope, maybe I should just check off these answers too. I hoped I answered them, but you can therefore answer a new one if you feel that it was you want some more. So, okay, how do we do this? Well, the way we do it is with a technique called implicit differentiation. So this tool called the implicit function theorem, which goes back again to Cauchy. I mean, it's not a new thing. Basically gives conditions under which the derivative of an implicitly defined mapping exists in a local neighborhood around the solution. And unfortunately, because all we care about is sort of local neighborhoods when we do gradients, gradient-based updates, this is sufficient to get a derivative, the derivatives we need. And so the basic idea is you write the fixed point condition at the solution. And here I'm writing y as a function of x because, of course, y will depend on the input x. I write that solution in terms of the fixed point, and then I just differentiate it. This is just, again, it's a technique called implicit differentiation. So someone asked, what are the alternative algorithms to solve deep machine learning problems? Why it has to be a concave equation? I'm going to defer that one because I think that makes I think that maybe it's conflating something. There's nothing about being concave here or anything like that. So let me defer that one until later. Keep asking by all means, but that one I'm going to take offline or shift to later. So we have our fixed point equation here. We differentiate it with respect to the thing we want to differentiate with, either the parameters or the input layer. And now we just apply the chain rule. And if we apply the chain rule to this, we actually just get two expressions. So first we differentiate this with respect to x, treating y as a fixed variable. Then with respect to y, then the derivative of y with respect to y. But again, here of just treating y as a fixed variable at the value y. And then this term pops out via the chain rule here. So this is just actually a simple application of the chain rule. And this is the key condition that has to be satisfied for these gradients in an implicit layer. But the big idea here, the big point is that these first two terms are actually just sort of normal explicit differentiation, in that all we need to do is just differentiate a function with respect to its arguments. And g, again, is defined as a natural function. The solution for finding this root is not, but g is. And so we can actually just, and if it's a deep learning system, you can actually typically solve those with, or find those themselves with ordinary automatic differentiation. And not just rearranging terms, we have an actual solution for the gradient we want to know about as a function of kind of ordinary automatic differentiation tools. And again, as I mentioned, this is a technique called implicit differentiation. It goes back many decades or centuries, and we can actually employ it very effectively to sort of solve our to incorporate these layers within deep networks. Now, this is a very sort of high level presentation of this topic here. If you want more information, I would suggest we actually did a tutorial on this topic very recently, and I would suggest you would look at our recent NeurIPS tutorial on this very topic. So we both have about two hour long video. This is myself and David Duvenat, who works on neural ODEs, and Matt Johnston, who's one of the core developers behind the JAX system. We have a set of video lectures as well as a sort of a very detailed set of slides and notes for this, along with code examples for all this. So we have a very detailed set of notes you can go through to learn more if you're sort of broadly interested in implicit layers as a whole. The one thing I will say, though, which is the point I actually want to make here, is that it's actually quite easy to do this, even in cases where you might think it is hard. So on the left here, I actually have a whole differentiable version of the CVXPy prototyping language for convex solvers. It's not quite complete, but in about this much code in PyTorch, you can create a differentiable version of CVXPy's or a version that can differentiate through CVXPy layers. This is a convex optimization modeling framework developed by Stephen Boyd's group at Stanford. And you know, in this much code, you can actually make a differentiable version of that, or at least a rudimentary differentiable version of that. So the big point I want to highlight, and most of this code, by the way, is just like manipulating matrices, like because you have to put them in a certain block form to invert them. So the point I want to make is this is actually not that complex, and a lot of the development we do can be written in this way. So a lot of code, a lot of very structured solvers can actually be, without too much work, transitioned to differentiable variants that we can include into deep networks. All right. So with that as sort of the background, let me now just give a quick, and I will be quick here because I do want to maybe have 15 more minutes with the question, or 15 more minutes including questions. I want to go through some of the work we've done on what we do with these implicit layers and how we actually use them in practice. So one of the first applications we actually used for these things was exactly the one I presented at the beginning of these slides here. It was a way of actually incorporating a optimal power allocation method into the loop of a stochastic energy forecasting predictor. So the idea is we were training a method to predict upcoming electrical demand from weather data. We would then use that demand prediction to schedule power generation over the next 24 hours. And then we would look at the costs incurred over this time period based upon different costs for having overgeneration or undergeneration of power. And the key point that I want to make here is that if you look at these two plots, the red and green lines are, the green line is our method for making predictions that are based, which we call task net, because it's sort of taking this task of optimization into account. And what we see is that the green line is about as good in terms of the root mean squared error of the forecasting. So it's actually you pay a little cost here in terms of forecasting precision, but it's almost as good. But what's very, very different here is that, especially as further forward where there's more uncertainty about demand, if you optimize the machine learning forecaster to take into account the optimization of the power allocation procedure and the actual cost of power allocation, you can drastically reduce the actual cost you have, i.e. the cost of generation or the cost in terms of CO2 emissions that you actually suffer when you run this procedure. And this is some work that appeared at NeurIPS a few years ago. We've also done some work in building differentiable physics engines as layers. So we had a work also at NeurIPS a few years ago on building a differentiable layer that simulates rigid body physics. It simulates the equations of motion of rigid bodies. And using this approach, we actually can use a differentiable model, can incorporate a differentiable model into reinforcement learning methods. And apply it to games like Breakout here, which is a sort of a well-known Atari game. And if we do that, because Breakout's actually kind of a physics game, right? It's about a ball, you're trying to balance this ball and break these bricks here. And because the network knows these physics and can actually exploit these physics, if we incorporate this layer into a deep network, we're able to learn to play this game with many, many orders of magnitude less data than we would need if we actually ran a more standard reinforcement learning algorithm like Q-learning. Now, of course, it's also much more limited in some sense in that, it is intended for these physics games. We also, to be clear, build in some basic object detection. So it's not a direct comparison, of course, but it's not directly comparable. It's not as general as Q-learning. But what we want to highlight is when you do build the system in and then still need to learn dynamics, we won't sort of tell it ahead of time. We just say, here's some physics, try to learn them. Learn how the player actions affect the ball, learn how the ball causes reward, things like that. We're able to learn it with 1,000 observed examples versus on the order of tens of millions for typical deep learning systems. We've also done some recent work on incorporating partial differential equations into neural networks, and in particular into graph neural networks. So a common task in PDE solutions is solutions of complex equations, in this case, that govern fluids. So this is actually the Navier-Stokes equations, precisely that I was alluding to before. The Navier-Stokes equations are very complex to solve. They're very simple to write, but again, very complex to actually solve. And there's been a lot of work on using things like graph neural networks to actually attempt to solve these things, maybe more efficiently than our state-of-the-art solvers. The problem, though, is that most graph neural networks don't know anything about physics. So they don't generalize very well to new settings of, say, an air. I mean, if you show it enough data, it'll be able to sort of replicate that same data. But if I tilt the wing a little bit, for example, it won't really know how the physics are supposed to react to that. And so what we do here is we actually combine a low-dimensional but differentiable PDE solver. And actually, a lot of PDE solvers are differentiable because in PDE solving, this goes by something called the adjoint method. So they've been doing backpropagation for a long time in engineering, certainly. And we incorporate, by this differentiable property, we were able to incorporate this PDE solver into a graph neural network that allows us to sort of build an end-to-end system that can use a very coarse PDE or a PDE solver at a very coarse resolution. Of course, we can't do it at a high resolution, or that's the problem we're trying to solve, right? We're trying to make that more efficient. So we use a PDE solver at a coarse resolution, incorporate that output, and actually adjust the mesh as we go, based on the coarse mesh as we go, into a graph neural network, and use that to predict the outcome. This is work that appeared this past year at ICML. And we show that it's both more accurate than a pure graph neural network approach and much faster than just running a high resolution PDE solver. Okay, so there was a question about how do you deal with nodes or layers like PDEs that have significantly higher computational complexity than others? What about parallelization? Yeah, so as I said, I'm sort of taking big, complex deep learning and making it even harder because we're putting in really complex layers that have to be solved literally every time you want to do a forward pass to the network. I think this is still largely an open problem. The best of dealing with these things, of course, some cases you just can't do it. You can't have a high resolution PDE solver in your network that those take days to solve as it is. That's not feasible. This is ultimately going to be a sort of an exploration of different approaches. So what we have done is we've spent a lot of time trying to come up with efficient implementations for these different common layers, like optimization, like ODE solving, things like this. That's more David's work on ODE solving, but this community, we've been doing these things. We've been trying to do a lot of work on building efficient, particular GPU-based versions of these things because the rest of the neural network is already living on GPU. And so if we can do these, and done in parallel because of mini batching. So if we can implement these solvers in a parallel way on the GPU, we can run them much more efficiently. So we have lots of work on that. For example, the work I mentioned in the power dispatch, that uses an efficient solver that runs on the GPU that can be batched over examples. And that's what makes it sort of efficient. But it's still very much an open problem how you do this well. Oh, so someone says, actually, I'm going to defer the question to stat solving because I have a slide on stat solving in 2 more slides, I think. So you picked a good question for me. Maybe it wasn't a plant, I promise, that question on stat solving. I'll be done with that one. Or you can ask later about that one, maybe. And the idea, okay, so someone also asked about if it's can be adapted to multi-step decision making. Yes, so absolutely. So a lot of multi-step decision making works in what's called sort of a model predictive control or receding horizon sense, where what you do is you sort of make multiple decisions and then adjust them, or you make your decisions based upon sort of forecasting out in the future, take one action and then do this, repeat this process. And there's two ways you can make it, you can sort of apply this here. You can just apply it because that multi-step prediction problem is an optimization problem. You can incorporate that into the system, take one step as the policy, and we actually have some work exactly on differentiable model predictive control. I don't think I have that here actually because there's too much to include. But the other answer is that you can also differentiate through multiple steps. So you can also make the whole thing like a big recurrent network in some sense and differentiate through the whole thing. That of course, brings added complexity, but it can be handled with this framework because, maybe not even anything special to this framework, just because you could handle kind of multi-step prediction with sort of standard recurrent-like structure in deep networks. All right, actually, so talking about this is actually a good lead into the next slide. Talking about reinforcement learning and robust control, or control in general. One thing, just like in my original example, where machine learning was not that often applied to maybe a lot of data-driven or advanced machine learning, so deep learning is maybe less applied to some sort of more statistically driven scientific sort of problems in general, but that's changing a little bit. It's also the case that reinforcement learning, while it has achieved some sort of amazing breakthroughs in recent years, Atari games and AlphaGo and StarCraft and Dota and these things, it's also the case that there's lots of control systems out there that people would never touch RL with. And the reason is that RL methods, while they get great performance, you can't really say much about their guarantees. They don't come with the same sort of guarantees you can give about domains, say, like robust control. And this is a big challenge, in fact, for applying RL to many safety-critical domains where you sort of where stability and the sort of classical control paradigms are really paramount here. So we have some recent work that's actually going to appear this year at ICLR on enforcing robust control constraints within a neural network. And this means that you can actually embed this then in deep learning algorithms and ensure that the deep learning system will obey robust control criteria like stability with respect to an unknown system, an unknown polytopic system, or H-infinity like norm bounds. You can actually guarantee the system achieves the same robust control specifications as traditional robust control while potentially performing much better on average. And the basic idea is that a lot of these robust control techniques come with Lyapunov functions. They are guaranteed to always decrease over each step. And what you can do with your over the entire uncertainty set, they're guaranteed to decrease this. And what you can do then with your arbitrary deep network is you can differentiably project this output into the span of sort of the allowable set of controls given to you by the robust learning algorithm. And this both performs better than traditional robust control policies, and it's safer than pure robust RL control. So just to dive into this one a little bit deeper, we have some examples here on I think this is a quadrotor example. We have a few. We also have a smart grid example on this one. I forget exactly which one this is. But basically, we have a bunch of non-robust methods here, like running LQR or actually running things like PPO, which is a reinforcement learning algorithm. These all do quite well, but they are, in the worst case, kind of non-robust. In contrast, robust control does robust control techniques like LQR, like robust LQR, can actually do quite well, but they don't perform as well on average as the reinforcement learning techniques. And our techniques here that we propose, they work well in the worst case, they're guaranteed to work still, while in the average case, they do quite a bit better. And this is a log scale, so this is actually quite a bit better than the traditional robust control methods. Okay, I see one more question here. The current slide sums it up well. The quest for accuracy and resolution with more limited data is much more neatly addressed with this hybrid approach with conventional ML methods, recurrent or otherwise. Yeah, summed it up great. More of a comment, I guess, than a question, but thanks. Wonderful. So maybe just a few more before we end here. Actually, I'm gonna just do one more since I want to stay close to time. Someone asked nicely enough about SAT solving, and it's a great question because many optimization problems I should care about in many domains like climate sustainability and many others are inherently discrete. Whereas, at least so far, I've been focusing on continuous settings. So everything's been continuous, right? PD simulations, optimization over continuous variables, et cetera. And I'm putting the domains of climate sustainability here because we actually applied some of those, but of course, there's many more domains as well. So Laura is asking about, is it to do with less parameters in an implicit network compared to a standard explicit one? That's a great question. So I'm actually pause and answer that for a second. It depends entirely, in my experience, on the type of structure you are embedding into the implicit layer. So in layers that the layers that we've actually talked about. So these are sort of like your implicit deep learning layers or our deep equilibrium models, which I'm actually not talking about in this talk, but for those that are interested, these are sort of an implicit layer that uses a more generic function f. Like a neural network function. So it doesn't really encode that much structure. It just uses an implicit root solving. It just defines the network kind of in terms of root solving. And of course, Laurent has concurrent work in this area as also. What we found is this entirely depends on structure. So when there is structure, explicit structure in a network, like solving an optimization problem or simulating physics and things like this, then you definitely can use less parameters in these networks that simulate it because they are effectively encoding known correct structure into the problem, or at least they're encoding some very strong bias that can reduce the amount of data you need and therefore the amount of extra parameters you need. What we also find is that when you have a more generic implicit layer, like a deep equilibrium model or like one of your implicit deep learning systems, then the parameter count almost always has to match exactly. So even though they work in very different ways, the implicit like network almost always requires the exact same number of parameters as the explicit network in order to reach the same level of performance. So there's a very seemingly fundamental kind of parameter performance trade-off here that is frankly still a mystery to us in deep learning, but which seems to also hold for these sort of unstructured implicit layers, even though we definitely get a benefit in terms of data and parameter efficiency when it comes to these more structured layers here. Okay. So let me finish this last point and then I'll be done. Someone asked about combinatorial optimization, and this is a big problem because I've talked about everything being differentiable so far. And a big problem about discrete optimization is that it's not differentiable by definition, kind of, right? It has non-differentiable components. If I change, even linear programming, for example, if I change my objective a little bit, it won't change the solution, right? The solution bounces around on edges of the polytope. If I change my cost a little bit, the solution is the same until it all of a sudden jumps to the other to another vertex on the polytope. And the same is true for integer programming, of course, for many other things like this. So how do you make these things differentiable? It's a big question. What I would advocate for here is that we have a very powerful set of relaxations for these problems that solve smooth variants of these combinatorial problems. Some of the most famous one are semi-definite relaxations of classical combinatorial problems like max-cut or max-sat programming. And so actually in some work we had at ICML in 2019, we embedded a differentiable variant of a SAT solver inside of deep networks. And this differentiable variant used a semi-definite programming relaxation of the SAT of the max-sat problem. And by doing that, we were able to solve problems like learning to solve Sudoku tasks from data. So not telling it how to solve Sudoku, giving it the rules, just giving it a bunch of examples of solved and unsolved puzzles and figuring out if it could solve it. And in fact, because this is deep learning, we can even do fun things like make Sudoku problems out of MNIST digits and still learn to actually play Sudoku from MNIST images where here's 0 is like the blank square. Fortunately, it's exactly 10 digits you need to do this. But by combining this, by embedding this sort of max sat solver into the network, you actually can solve these combinatorial problems or smooth the approximations of them within a differentiable framework. But I admit this is still very much an open problem how you do this, and there are lots of different sort of techniques for this. Okay. So let me conclude with some final thoughts. So I think there has been historically a disconnect between what I would call it the scientific community and the ML community in terms of the methodologies and the key requirements of models. And what I want to argue for at a high level here is the tighter integration of these two sets of methodologies. I think deep learning has achieved some amazing things, including some scientific breakthroughs like the AlphaFold and things like this. But I think really seeing machine learning be applied everywhere requires that we meet the constraints of the engineering center communities in a more formal and foundational way. And this does not simply have to be a method of us kind of bolting on machine learning approaches to existing engineering processes, or maybe applying naive or either bolting on kind of the engineering knowledge into ML or bolting on ML into engineering practices, right? I think this is not what we need. What we need is tight integration of these two components, and that can often be achieved sort of very well through this notion of embedding very structured layers into deep learning systems. Not the only way to integrate it, but I think it's one very powerful technique for doing this integration. And I think as a final thought, what I would say here is, I think there's much more room for exploration here. We're only getting started, but there's also a lot more room for even thinking beyond this. When we talk about topics like health, right, which is again the subject of a lot of these lectures, we have many sort of modes that go beyond simple models. So there's complex, policy making when it comes to health issues is not going to be the result of an optimization problem. It's a very complex thing that involves a lot of factors. And I think it's going to be one of the big challenges for these methods is how you actually incorporate more uncertain, more unknown results or decisions that are made using machine learning and AI systems into sort of the actual training process and the actual system, the actual learning process of these models themselves. And so I think, we want to move more and more towards what I would call sort of truly end-to-end systems, things that really take into account the whole life cycle of a machine learning model. And I think this is one small part of it, but I think we're really just getting started here, seeing truly what machine learning can accomplish when we integrate it holistically in these settings. So thank you very much. I guess I went a little bit over time, but there were some questions during the topic, so hopefully it's okay, Shankar. And
fantastic, Zico. That was a fantastic talk, as you certainly lived up to. Let me make sure that there's no other questions, because there has to continue to be some questions about.
Yeah, there are a few more.
Take one of them. Yeah, I think we'll get a few of them before we sign off.
That I can take. Yeah. So Shavik asks. First of all, hello. How are you doing? Shavik asks, what happens if the prior knowledge physics is wrong or contradicts the data? Can we balance listening to knowledge versus listening to the data? It's a great question. So far we haven't thought about that too much. We've thought more, frankly, about cases where we have some at least rudimentary understanding of the physics that we sort of want to, or knowledge of the system that we really do want to embed. Having said that, some of them can deal kind of okay, just because models that are wrong still work quite well in practice. If a model's a little bit wrong, all models are wrong to a certain extent, right? Some are just more useful than others. I think that's like a saying in statistics or something like that. I forget that's a quote from somewhere, I believe. The point though is that if our knowledge we're embedding is wrong, you have this sort of same question of sort of the bias variance trade-off of normal machine learning, or you're coming back to something very similar, right? Where your algorithm will be biased to sort of make certain answers to these questions that really are kind of constrained by the allowable data and the allowable knowledge that you have. Sorry, not the data, the allowable knowledge you have. And we haven't really thought about like smooth ways to sort of relax that and go to a more purely data-driven model as you get more data. You can, I imagine, do it in a number of ways that sort of I could think about offhand, like having sort of, you know, treating your physical system more as like a prior and incorporating additional information from, you know, building up a posterior. If you have more data, you can kind of do that with some sort of Bayesian approach, but we haven't thought about it too much. So I think it's still very much an active question. Okay.
You want to get the one on transparency, Karen?
Yeah, so I see it for control-related problems. I thought that's what we're missing in the control community. Oh, just a comment. Well, thank you. So I'm really excited about the connections between control theory and these methods here. I think it's a really fascinating area. I mean, in general, learning and control is a hugely interesting area, and I would love to see sort of more research in that direction globally. I think there actually is a lot more. There's this L4DC conference and things like this that are really starting that community, which was at Berkeley, or was going to be at Berkeley last year, but unfortunately could not be.
It was held virtually, and next year it's in Zurich, virtually maybe.
Yeah, it's gonna, well, maybe, right? Is it gonna? Oh, is it gonna be virtually this year for sure? Right? Okay, got it. Yeah, there's a question. So Karen asked a question about transparency. Yeah, especially when end-to-end from data decisions to make the process less transparent to, well, okay, does end-to-end learning make the learning process less transparent to humans? Yes, it probably does when it comes down to it. There are extents to which it is very likely true that as you do more more end-to-end aspects of this, then more sort of parameters can be tuned in a way that is a little bit opaque to humans. I think actually some of these implicit layers can make the system still better than purely generic deep learning systems because they do actually have structure in there. And so a big advantage in some sense is the fact that you can embed quite a bit of knowledge and therefore sort of understanding and intuitive nature into these systems. But you're absolutely right that when you move toward an end-to-end learning framework, you may very well have components that are tuned to sort of in odd ways that are very hard to understand in some sense. So I think the choice of where you draw the line and where you start the tuning and where you want the feedback loop to be is ultimately in practice, of course, going to be an engineering decision you have to sort of balance with other constraints of the problem. So I think it's sort of a bit of a wishy-washy answer, but I think it depends is the right answer there to a certain extent. So someone mentioned that someone asked, is SatNet really an implicit layer? Yes, it is. So SatNet is solving a max cut semi-definite program, and that layer is implicit. It is solving an optimization problem. It is defined in terms of an implicit set of equations that you solve at the solution. So it is absolutely an implicit layer. It meets the definitions of all of them. It seems different as the problem. So yes, it's learning a problem, but the layer itself is an implicit one because it's defined in terms of solving a semi-definite program. It isn't solving Sudoku. The layer is not a Sudoku solver. It is a satisfiability solver that is set up in terms of a semi-definite program, which is itself an optimization problem, which is an implicit condition, which has implicit optimality conditions. Where can we learn more? Okay, great. So first of all, it's not sharing anymore, but my website is easy to remember. It's just my name, zicokolter.com, so you can easily remember it. You don't have to Google it even, or if you Google it, you've already done too much, right? You could have saved yourself a space and gone from there, but you can also Google it. I have a lot of text on my website, as well as that implicitlayerstutorial.org that I mentioned. Maybe I'll just send out that message here. So I'll just type the two websites that you might want to, this one's the easy one, but then the other one has a lot of information on implicit layers in particular, much more, I should say, like mathematically detailed than this and code driven than this, is implicitlayerstutorial.org. And so you can go there and check out a lot of the resources we developed for the last tutorial in NeurIPS last year. So I'll keep going, or should I stop?
I think. Why don't you just take one or two? Because
okay, I'll take one of the last two questions here. Do you have an, okay, what are the thoughts on bias, knitting, propagated, or amplified? Okay, very different questions. Second one I can answer very quickly. So I'll answer the second one first, and then we'll get to the first one. The second one is where these layers go. In practice, they could go anywhere. Or sorry, in theory, they could go anywhere. In practice, because the input to the network and the output of the network are the things that we have the most grounding, they typically go as the first layer or the last layer in these networks, either processing the output or processing of the input. We've done a lot less with sort of incorporating them. These sort of very structured ones, we've done a lot less as incorporating them kind of as intermediate layers. And the last question, boy, on bias in data being propagated or amplified in machine learning. This is a huge, a hugely important problem. One which I think is not directly addressed this work, except to say this notion of sort of transparency of the models. These models might be to a certain extent more transparent than existing techniques, because they do have some physical grounding. So you might be able to at least identify components where a bias might be being amplified or being introduced by an algorithm. But the reality is this is a hugely complex problem, and one that I actually have other students working on sort of a little bit outside this work, which I think is really going to be one of the foundational problems in machine learning going forward.
Fantastic. Zico, that was wonderful. And I really love the way you answered the questions. The hard work monitoring and answering.
Oh yeah, no, I get good at this for courses, right? So I have to do my courses. So I've gotten good at like looking down constantly to monitor the chat in Zoom.
Hey, that was a wonderful set of things to look at. I held my own questions, but I think I'll get back to you. This a colleague of ours here called Yi has also been pushing.
Yep.
Okay. Anyhow, I was delighted to listen to you answer the other questions. Great talk as always. Thank you very much.
Thanks very much, Shankar.
Thank you. Okay.